Okay. So what is the name for the pumps that actively keep more sodium outside the cell and more potassium inside the cell? Most of you went with B, sodium potassium pumps. That is absolutely correct. Some of you went with voltage gated pumps. Those we are going to speak more about today, but voltage gated pumps are what create the action potential. So they are not responsible for keeping the cell in terms of the resting membrane potential, keeping the cell, um, keeping the relative proportions of the ions, keeping sodium being in excess outside the cell and potassium excess inside the cell. So the sodium potassium pump is going to be responsible for that. That's why we said that it's going to be responsible for 20% of the resting membrane potential, because it helps to keep those relative proportions. All right, so B was the answer here. Let's move on to a second question. Okay, about 10 seconds left. All right. Okay, neurons are generally more negatively charged on the inside than the outside of the cell. What is the name for this difference of charge when the cell is at rest? Okay, perfect. Everyone got this correct, and I was hoping that no one got this wrong. So this is the resting membrane potential. It's pretty much a basic definition of the resting membrane potential. Neuronal charge, not so much relevant. We know that all neurons have a separation of charge, but that is not what's being described. Equilibrium potential is also not what's being described. We know that that is the potential at which an ion is at equilibrium. In other words, it has zero movement because both forces are equal and opposite. And then d-ionic phase shift, also not relevant here. Okay, let's move on to a third question. All right. Why does the resting membrane potential tend to be closer to the equilibrium potential of potassium than that of sodium? A majority of you went with D. D says the electrochemical force of potassium is stronger. So this is not correct. Let's see. Some other folks went with C. The membrane potential is more permeable to potassium. This is true. Okay, let's see what B says. Potassium's concentration gradient is much bigger. Not necessarily. Okay, not necessarily. Potassium concentration gradient is much bigger in what way, right? The concentration gradient for potassium is actually out of the cell. And then it has an electrochemical gradient in the opposite direction. So its concentration gradient is not necessarily bigger. And the potassium has a stronger charge, not true as well. They're both positively charged anion, cations, okay? So the answer here is C. And just to explain this a little bit further, remember we said at rest, the membrane potential is negative 70 millivolts, which means that there are more negative charge particles inside the cell. The reason this is so close to potassium's equilibrium potential is because there are more doors or channels for potassium. Remember, the equilibrium potential is the force with which the ion wants to move in order to get to equilibrium. So if we have a really low or a really negative membrane potential, which is negative 70, it's much closer to potassium's equilibrium potential of negative 94, simply because there are more channels on the membrane to allow potassium to move more freely. All right. The opposite is true for sodium. Sodium has a very positive equilibrium potential, which means that way up high at positive 60 is where sodium will be at equilibrium. And so that's really far away from the resting membrane potential of negative 70, which is to say that there's not a lot of opportunities for sodium to move. There is less of a membrane permeability for sodium. Okay. Any follow-up questions to those items? Please go ahead and drop them in the chat box. Otherwise, we're going to keep on moving. I think we got to speaking about the channels on the membrane. We drew them out and illustrated them at first, but then we just described them. This is where we left off. We spoke about leak channels, always open throughout the membrane. In fact, these are the channels that we speak about when we talk about the relative permeabilities. So they're going to be more potassium leak channels, right, which allows potassium to more freely move than there are leak channels for sodium. And they're always going to be open. They're found throughout the neuron. And these are indirectly responsible for the resting membrane potential. Remember, the sodium-potassium pump is responsible for 20% of the resting membrane potential. And then the leak channels, because there are more potassium, which allows more potassium to leave than sodium can come in, is indirectly responsible for 80% of that resting membrane potential. We also spoke about the ligand-gated channels. These are channels that needed a requirement or condition to be met in order for them to open, specifically a ligand to bind. Also, voltage-gated channels needed a specific voltage threshold to be met for these channels to be open as well. The voltage-gated channels are going to be throughout the entire length of the axon, but a little bit more concentrated at the axon hillock. And these are the channels that are monitoring the threshold of the signals coming in from the soma. If you think back to that illustration from Friday, the signals, the graded potentials, which are smaller changes to the membrane potential, come in onto the soma. They get measured at the axon hillock by these channels, and then the voltage-gated channels are responsible for initiating that action potential. Lastly, were the calcium channels. These we said are on the axon terminal, so the very distal end of the neuron, and they're going to release a neurotransmitter that is going to convert the electrical impulse of an action potential to chemical energy. So this is a really important transference of energy that happens at the end of the neuron, where we go from electrical, i.e. the action potential, to chemical, which is the release of a neurotransmitter, a chemical, that can cross the synaptic junction, all right? And then that can relay that message or communication to the adjacent neuron that will be reconverted to a new action potential. So we're gonna go from electrical to chemical as a way to keep this flow of communication going from neuron to neuron, all right? So let's talk about the ion gating along the axons. So when we think about the length of the axons, this is where we have exclusively the voltage-gated channels. We'll talk about some voltage-gated potassium channels, as well as some voltage-gated sodium channels. So there are two types of channels on the membrane. This is kind of where we want to make that distinction. Potassium has the not gated leak channels that are always open. This is just recalling here that this is how we have the increased permeability for potassium. Potassium also has gated channels, which are open when there is a specific membrane potential threshold reached. They're going to be closed typically when the neuron is at rest. But again, once we get to that specific membrane potential threshold, these channels will open up and they're going to be responsible for certain aspects of the action potential. We can compare that to the sodium channels. Again, all throughout, we have a few leak channels, not as many as we have leak channels for potassium, but we do have a few sodium leak channels. And then more specifically along the axon, right, pertaining more to the action potential, we have sodium voltage gated channels that are, again, closed at rest, but then they are permeable or become open whenever we get to a specific membrane potential threshold. So these are some things to bear in mind as we go on to really describe the gating mechanisms. We're going to talk about the gating mechanisms for sodium. In other words, what are the conditions that are required to open up voltage-gated sodium channels? What are the conditions required to open up voltage-gated potassium channels? And so I want you to be distinguishing this channel from the leak channels that we have talked about before, because leak channels do not require any specific mechanism or requirement for them to be open. So really want to make a distinction between these two types of channels as we go on to speak more about the gating mechanisms for each. So first off, let's begin by looking at the voltage-gated sodium channels. These channels will open when the membrane potential gets to -55. So here is where we get our threshold value from. This is the value that must be met in order for us to trigger or initiate an action potential. This is why it's so important to note this value, because until we reach this value, we cannot open up the voltage-gated sodium channels, and these are the main channels that are required for the action potential. Okay, upon opening up these channels, sodium is going to rush into the cell. Think back to the ECDF for sodium, right? The electrochemical driving force for sodium. It's into the cell, strongly so, because its concentration gradient is into the cell. Its electrical force, electrical driving force, also into the cell. And we talked about combining those two values, right? 60 plus 70. So we have a really strong driving force to move sodium into the cell. And if we were to open up additional channels, we would see sodium rush into the cell according to that gradient. Upon that, the membrane potential is going to start becoming more positive, okay? Okay, so really great question here. Let's kind of slow down and backtrack a little bit. In the chat, I've got a question. What does it mean to depolarize to -55? Okay, excellent question. Let's go back a bit to look at the graded potentials. Okay, because understanding the graded potentials is really important for understanding how we get to that -55. So remember we said that graded potentials were smaller changes in the membrane potential that are coming in on various points of the soma, of the cell body of the neuron, okay? So we can have maybe a tiny change, maybe about 10 millivolts, maybe another 10 millivolts. So these graded potentials are always coming in from the neurons that are synapsing onto the soma of that neuron in question. If we have, let's go back to this slide here, the fact that we can sum these smaller graded potentials. So let's say via temporal summation, we have repeated stimuli coming in onto that soma, and we add them together, right? We can sum them or add them together, and that is enough of a membrane potential change to get us to that -55. And when I say -55, I'm talking about the membrane potential change. It starts off at -70, and via the changes occurring through these smaller graded potentials, we can add them up together, and now we have arrived at -55 millivolts. This is our threshold because after we get to -55, we're always going to fire an action potential. Okay, later on, we'll talk about the various features of an action potential, but one of those features is that it is all or nothing. Either we have met the threshold and we're going to fire an action potential, or we have not and we won't. Okay, this is where we again want to distinguish between a graded potential, which is varied in its magnitude, small and not sustainable, like it can't propagate across lengths of the neuron, versus an action potential, which it's a bigger change in the membrane potential and it is sustainable. So it can now propagate down the entire length of the neuron. Okay, so really great question to help us really just clarify some of the fundamental understanding that's required for what we're going to talk about now. All right, so we have depolarized to threshold. Because of the summation and the smaller graded potentials that have aggregated, we have gotten to our threshold value. Now we open up one of these voltage gated sodium channels. When we do that, sodium rushes in. The membrane potential is going to start increasing. Remember, sodium is a positively charged ion. It moves into the cell. And so now we are no longer seeing a -70 as far as our membrane potential, because all this positive ions are rushing into the cell. So the membrane potential starts to become more and more positive. Remember, just kind of thinking back to some of the basics that we discussed before. When we talk about the membrane potential value, it is describing the inside of the cell relative to the outside of the cell. So as more of that sodium rushes in, the inside becomes more positive. Okay, another important thing to remember or to say about voltage-gated sodium channels is that they then become deactivated at +30. Okay, so not only is there a membrane potential value required to open these channels, but there is also a membrane potential requirement that allows these channels to close. So they're going to open at that threshold -55. We're going to have sodium rushing in, rushing in, rushing in. When we get to +30, that membrane potential is going to automatically deactivate these channels. All right. Now, if you look at our panel here and sort of compare what we just said to what's happening in the images here, here is our channel. Here is the inactivation gate. So we're going to speak a little bit more in detail about this specific channel. So it has an inactivation gate and it has an activation gate. So it's got actually two gating mechanisms that are at play. So when the cell is at rest, the activation gates are closed, right? In other words, sodium cannot move through. The inactivation gates are actually open, and the inactivation gate is open because this is saying that if we were to get to our threshold value, this channel would be ready to open up. So the inactivation gate is open and waiting for us to meet that -55, and then we're going to open the activation gate and sodium can flow through. So we depolarize the cell, we open up the activation gate. So now both gates are open, and we can say that the channel is now open here. Sodium can rush from the extracellular environment to the intracellular environment. That's going to change the membrane potential to become more positive. It's going to try to approach the equilibrium potential for sodium, which we know to be +60. So it's going to attempt to approach that +60, but when it gets to +30, which is about halfway there, another gating mechanism is going to be activated. That is that at +30, the inactivation gates will close. Okay, so once the inactivation gates close, the gate is pretty much, the channel that is pretty much inactivated. So the activation gates are open, but the inactivation gates are closed. And so the channel is closed and it's not capable of opening until we get back down to our resting membrane potential. Okay. So let's describe that a little bit more here on this slide as well. So we have the activation gate, which is voltage dependent, opens at threshold, which is -55. After that opens, the entire channel can be said to be open because both the activation gate is open and the inactivation gate is also open. The inactivation gate is voltage and time dependent. Okay, voltage and time dependent. What does that mean? That means that the inactivation gate is going to open at a specific threshold, but there is a timed component here. So after 1 millisecond, it's going to close. And the reason it's going to close after 1 millisecond is to close the entire channel so that sodium can no longer move through the membrane, but also to prevent another action potential from coming along right behind this one. All right. So the activation gate is voltage dependent only, but the inactivation gate is voltage and time dependent. So after 1 millisecond of the activation gate being open, the inactivation gate automatically closes. And so the channel is pretty much inactivated in this state, to where if we had another negative 55 millivolt change, we could not fire another action potential until 1 millisecond has passed and the cell gets back to rest, which is this state where the activation gate is closed, but the inactivation gate is open.